Wave. Everybody's got a wave. You know why? Because it just makes my heart get warmer when I see people waving. Doesn't have the same effect if it's live. I don't know why. Look into that at some point. Yeah, see, that's fine, but I just don't feel like the heartwarming effect. Don't get me wrong, it's okay. But yeah, so there you go. You get one back. Gregory, how you doing? Okay. Don't touch anything today. Okay. All right. Here's what we're doing practice, and we're moving on. We've got change in internal energy. We need to know heat loss or gain. Sign values are important. We need to know work. Was the system doing work on the surroundings by expansion, or was the surroundings doing work on the system by contracting the volume? There's a sign value associated with each. Obviously, if the sign value is off, then your answer is going to be off. So sign values are really important here. They're always important, but they're especially important in thermochemistry. Okay? When you do work against these surroundings and a gas expands against some sort of pressure, the sign value from work is going to be negative. If it's the opposite of that, if the surroundings are doing work on the system and compressing, sign value is going to be positive for work. Q is kind of easy because it's all related to the system. If the system is taking in energy, it's positive. Positive here. If the system is losing energy, it's negative. It makes perfect sense. If you remember, the frame of reference is the system. Positive or negative relative to energy gain or loss by the system. Okay? Have at it. We want our final answer in joules here. So we want joules. And so we need this conversion. Notice 1 liter atmosphere equals 101.3 joules. Here's my initial. This is my final. Notice we're doing work against the surroundings. So there's the pressure that we're doing work against. Notice my formula here, Q plus W. Notice Q is heat loss or gain. Notice we are gaining the system here. Let's just write it. And there's the surroundings. Notice the system is gaining energy in the form of heat, so that's got to be positive. The Q is the easiest one to come up with sign values. Well, work, we could write the formula for work maybe right here. If you can see it at home, not sure. Back up a little bit. Work equals negative P delta V. So this is negative P delta V. Volume or changes are always going to be final minus initial. So notice the final is 4.00 liters. The initial is 2. So we have a change here. Our change is going to be 2.00 liters. That's our delta V. And notice we're doing work against a certain amount of pressure. And that value is, of course, if it was in mmHgs or torr or kilopascals, we need to convert it. Why? Because look at that, conversion's in liter atmospheres. Okay, so just convert to atmospheres, whatever the pressure is given, just nothing new there really. So that's 1.2. Sign values important. So notice, see the negative here. It's easy to forget that little sucker right there. It's easy to forget that. So let's do this. Work equals that. What do we have here? What's our answer in liter atmospheres? By the way, let's squeeze in, that's ATMs. Liter atmospheres, and then of course we can convert liter atmospheres to joules. So 2.4 liter atmospheres, but let's convert it to joules here. So that equals negative 243 joules. So we're adding 500 joules from the surroundings to the system, and then we have this much work being done by the system on the surroundings. And we're going to have a change in internal energy of 256, and that is joules. We'll put a, 257 for sig fig purposes. So there's our change in internal energy. And that's our change in enthalpy, because we're treating the two identically, even though technically they're not. .4 liter atmospheres convert to joules. Make sure we understand our sign conventions here. Again, the math here, with this, the math gives you the proper sign. Okay? But I like to think of it as, I don't know. I think of this expansion, that just kind of reminds me of an exothermic process where the energy is expanding out. And that kind of reminds me exothermic is negative. So that kind of reminds me that this expansion is negative. Just a simple little way to help you remember the proper sign value. Go ahead and star that. That's about as hard as it gets. Make a note that these are related to each other, but they are not the same. So heat versus temperature, they're related to each other, but they're not the same. Heat is going to be measured in either joules or cals. So we could put that in parentheses. And temperature is degrees C, or I hate to do it, degree F, or Kelvin. Obviously, if they have different units, they are not the same quantity. They're not the same thing. You could have kJs, which is quite often in this class, or kilocalories. And again, degree C, Kelvin, or degree F. Well, if I have a small glass of water that's at 90 degrees Celsius, let's say it's got 50 grams of water in it, which, by the way, if you're dealing with H2O with pure water is 1.0 grams per milliliter. So 1 milliliter equals 1 gram. So just by measuring the volume in mils, if it's pure water, now be careful if the density of the water is like 1.2 because you put salt in it, then this relationship doesn't hold true. You just got to do a little bit more algebra with D equals M over V. But with water, because it's 1.0, 1 mil equals 1 gram, okay? So let's say we have 50 mils of water equal to 50 grams, and you're at 90 degrees. It's going to have a high vapor pressure at 90 degrees. You'll be able to see the steam coming off of it. Now, so we're holding that, and then we've got a bathtub that's completely full of water at 50 degrees Celsius. Okay. The bathtub and the small cup of water are obviously at different temperatures, but the amount of heat contained between the water in the small cup at the higher temperature and the bathtub, there's no comparison. The bathtub contains much more heat compared to the other, even though we're at different temperatures. Why is that? Because there's a big difference in mass. Big difference in mass between the two. Heat and temperature are not the same, but of course they're related to each other. Well, let's write the formula that relates Q, which is heat loss or gain. What do you know about that? It was right here a moment ago. That relates Q to temperature, okay? So Q equals ms delta T. So Q equals ms delta T, and this is Q is heat loss or gain. If Q is negative, that's equivalent to exothermic situation where heat is going from the system out into the surroundings. In other words, the system is losing energy to the surroundings. You're in the surroundings, so you're heating up. Okay? If Q is positive, we have an endothermic situation where heat is going from the surroundings into the system, and if you're out there in the surroundings, you're getting colder because heat's traveling away from the surface of your skin, and that gives you the sensation of cooling down. Well, so let's see here. Let's go with a beaker of water, and we have 100.0 mils, which equals 100.0 grams. Love that conversion. Let's say this gains, we've got heat. Let's say this gains 900.0 joules. We want to know the temperature change when this much water absorbs this much heat. But in order to do that, we need to know what S is. So let's write S. S is the specific heat capacity. So specific heat capacity. The specific heat capacity is a physical property that's every bit as important as density is. So you can use the specific heat capacity as kind of like a fingerprint for the substance. So silver, mercury, lead, water, any carbon tetrachloride, any sort of liquid, they all have their own individual specific heat capacities. Okay? Again, it's an important physical property. Really important. What are the most important physical properties? Well, melting point, boiling point, specific heat capacity, density, those are all really important. Electrical conductivity, if it's a metal, really important physical properties. Okay? Well, what is the specific heat capacity for water, for liquid water? S equals 4.14 joules over grams times degrees C. So joules over grams times degrees C. Actually, squeeze in an 8 here. I knew that looked a little bit off. So 4.184. Bless you, my child. So that's for liquid water. Now look at what we have here. We have heat loss or gain. Put an X there, just like it's PV equals nRT. We have Q right here. What's the sign value on Q? Q's positive here. Look at, this is an endothermic process. This is the system, and the rest of the world's the surroundings. Do we know the mass of the water? Of course we do. Put an X there. Do we know the specific heat capacity of the water? Of course we do. 4.184 joules per gram per degree C. And notice we can easily figure out the change in temperature. Go ahead and do it. And my little diagram, I'm just kind of running out of space here, so. Does this all cancel? Everybody, I hope everybody's okay. We just simply solve for delta T. This is going to be a positive value because energy was being absorbed by the system. Let's see. Joules cancels. Grams is on top. Notice grams is in the denominator there. Notice degree C is in the denominator of the denominator. And if it's in the denominator of the denominator, then we bring it up to the top. And sure enough, that's exactly what we have. So we've just increased the temperature of the water by 2.151 degrees C by adding 900 joules of heat to it. Be careful. What if this gave you the original temperature at 20 degrees C? So go ahead, write, what if the original temperature of the water is 20.0 degrees C? What's the final temperature? So the original temperature is 20.0 degrees C. What's the final temperature? Now, what I suggest you do here, if you know what's going on, you know that the starting temperature is 20.0 degrees, right? You know that. You know heat's being absorbed, right? The temperature has to go up. So what I suggest you do, figure out the change in T, and if you know what's going on, you simply add that to the original temperature because you know the change, you know that the final temperature is going to be higher than the original because you're gaining energy. Do you get the idea? What if we were losing energy and you figure out delta T? If it's an exothermic process, if you're losing energy, then you'd subtract from the original temperature. That just saves you a little algebra in terms of, okay, set this equal to delta T, T final minus initial, etc. So in other words, if you know what's going on, it's pretty straightforward. Does the final answer make sense? We went from 20 to 22 approximately. Energy was absorbed by the system. Yeah, it should have gone up, and it did. Then maybe go through the calculation one more time. Just make sure you didn't plug anything in wrong. And then you're pretty confident there's your final answer, and that's correct. Now, I went to 3 sig figs because the original temperature of the water was 20.0. So that had 3 digits. Okay.